Okay, so we've looked at how we work out the resistance in resistor networks. What we're going to look at now is how does Ohm's law work inside a resistor network. So we're going to start by looking at resistors in series. So we have here our 1K and our 6.8K resistor in series. So the total resistance in the circuit is 7.8K. And we have it hooked up to a 9-volt power supply. So let's take a look at the voltage in the circuit. So across the whole circuit, so if we go from the input and the output, we have 9 volts. That's what the power supply is putting out. That's across the whole circuit. Now, does that mean that this is going to be 9 volts and this is going to be 9 volts, or is this going to be less than 9 volts and some other value? Well, let's take a look. So across our 1K resistor, we have about 1.15 volts or so. And then across our 6.8K resistor, we have 7.92-ish. So basically it's in proportion to the size of the resistors. So we have the larger resistor has a bigger change in voltage across it. That's called a voltage drop. So the voltage drop across this 1K resistor is smaller than the voltage drop across the 6.8K resistor. And it's going to be equal, if we add those two numbers up, we should get the total of 9 volts again. Now, in this circuit, the resistance is of course fixed, but what about the current? So we have a current coming into the circuit and out, and it's flowing also in between. So is the current here different from the current here, different from the current here? Well, let's find that out. So what we'll do is we'll switch our meter over to milliamps, and we'll start what the current going in is. So what is the current coming into the circuit? So we'll go there, and because we're doing current, we're in the circuit. So it's about 1.16 milliamps going in. Okay, so we have 1.16 milliamps going in. Let's connect that back into the circuit there. Now let's check what it is across here. So let's take this wire out, and then we will check again. And again, we have 1.16 milliamps. So far, the current is the same in both points in the circuit. So finally, once we get this back in there, we'll check here. What's the current going here? So from here down to minus, and it's 1.16 milliamps. So in a series circuit, the current is the same at all points in the circuit. The voltage changes depending on the resistance at various points in the circuit. So the larger resistance, the larger the change in voltage. The changes in voltage will add up, of course, to the total voltage across the whole circuit. We had 9 volts coming off our power supply. And then from here, we measured our current, and we measured it at 1.16 milliamps. We also measured that here at 1.16 milliamps, and here at 1.16 milliamps. So everywhere in the circuit, for a series circuit, the current is the same. Now, how close this is to if we were to use Ohm's law on this is that? Well, Ohm's law is V equals IR, right? And if we don't know the current, but we do, in this case, we know if we were to work out theoretically, we don't know the current yet, but we know that the battery is 9 volts, or the power supply is 9 volts, and we have 2 series resistors, which gives us a total resistance of 7.8 kilo ohms. We just have to work out current by dividing the voltage by the resistance. So in this case, we have 9 volts, and we divide that by the total resistance, which is 7,800 ohms, and that gives us a current of 1.15 theoretically, which is pretty dang close to this here. Now keep in mind the actual resistors aren't going to be exactly 7800. So that'll be milliamps. And so pretty close to what we would expect if we just add these two up. Now, we also look at the voltage drop across the whole circuit. It's 9 volts, and that's what we measured, because that's what the power supply gives. But we also measured the voltage drop off these guys. Now, we measured this one at 1.15 volts, and this one here at 7.92 volts. So how does that compare to what theoretical values would be? Well, in this case, E is equal to IR, right? Because we know our current, and we know our resistance. So V is going to be equal to, now if we take the measured current, we can set 0.00116 amps times 1000 ohms gives us 1.16 milliamps, which is exactly what we had there. And then here at resistor 2, oops, that should be volts. That's volts, which is pretty close to our theoretical, to what we measured. Again, because the actual resistor is probably not 1000 ohms. Then if we do our second resistor, 0.00116 amps times 6800 ohms, we get 7.76, oops, 7.88, looking at the wrong formula here, 7.88 volts, which is, again, very close to that value there. So we can work out all of these by just doing Ohm's law. We just have to remember that Ohm's law will apply to the whole circuit, and then to parts of the circuit. We can do the parts. We can actually work out the voltage that the resistance that was actually there by going R equals V over I. In this case, that's going to be 9 volts over 0.00116 amps. That gives us 7.76K, which is pretty close to our 7.8K, given the resistors. I bet if we measured those resistors, we'd get 7.76K. Okay, now we're going to look at a parallel circuit. So we have our same two resistors, a 1K and a 6.8K resistor, and they're now in parallel. So we have the power coming in here and going out here, and they're parallel. So the total resistance of this circuit is around 870 ohms because, again, they're in parallel. So what does things look like here? Well, let's look at the voltage drop. So across the whole circuit, we have a voltage drop of 9 volts, which is what the power supply is. Across our 1K resistor, the voltage drop is also 9 volts, and the voltage drop across our 6.8K resistor, also 9 volts. So this is why things like our houses are wired in parallel. That way all our light bulbs get the appropriate amount of power and voltage. Now, what about the current? So is the current different in different parts of this circuit? So what we'll do is we'll check the current coming in. So we'll take this out just for a moment, put it here, and then let's turn our meter to current. milliamps. There we go. And let's take a look. How many milliamps are going through this circuit? About 10 points, about 10 and a half milliamps. So 10.5 milliamps are going into the circuit. And let's get this back in here. There we go. Coming out of the circuit, we have also 10.5 milliamps. So in and out's the same. How about into our 1K resistor here? So we'll take that out of there. And let's see what the current through our 1K resistor is. Here, it's less. It's about 9.2 milliamps. And on the other side, also about 9.2 milliamps. How about through our 6.8K? Let's get that out of the way. Yeah, let's take a look at that one. Ooh, that's 1.3 milliamps. And at the bottom, we have another 1.3 milliamps. So basically, in this circuit, again, the resistance doesn't change because they're fixed resistors. Because we have the same voltage drop across both resistors, we have to have a different current going through each resistor in order to make up for that. Looking at our parallel circuit that we just did, we measured the current through the whole system at 10.5 milliamps. The voltage drop across both resistors is 9 volts, which makes sense because they both see the battery completely. So there's 9 volts. That means that the current that comes through these is going to be different. Now, we measured those, and the current from here was at 9.2 milliamps. And the current here was measured at 1.3 milliamps. So how close would these be to the actual values? Now, the voltage drop is easy to compute because it's just going to be 9 volts, just whatever the power source is. The total current, we need to work out the effective resistance of this parallel circuit, which we did in our video on ohms on resistor networks. And so if we basically work out the voltage over the resistance, that's going to be 9 volts. And we worked it out at 872 ohms for the parallel network. That gives us 10.3 milliamps. So pretty close. Again, the actual resistance is going to be off a little bit because here we're using theoretical resistor values that are perfectly on point, whereas real resistors aren't exactly on their resistance values. What about these values? Well, again, we have the same voltage drop, and we just have a different resistance, and that makes sense because V equals IR. If V doesn't change and R does, to keep this balanced, I needs to change. So let's work that out. So in this case, we want to work out current again. So we're going to take the voltage, which is 9 volts, and we're going to divide by, in this case, our 1 kilo ohm resistor, so 1,000 ohms. That gives us 0.009 or amps, or 9 milliamps. Again, very close to our 9.2, which is what we measured. Then we can work out through the other one by simply going 9 volts divided by 6,800 ohms, which gives us 0.0013 amps, or 1.3 milliamps, which is almost exactly on our what we measured. So that is how we can work out this parallel circuit, and we can use Ohm's law and apply it there. We can just basically look at each of the resistors as their own little resistance, and if we're working out the entire circuit, we have to work out the effective resistance, or the total resistance of these two in parallel. So that's making that fairly straightforward. Okay, lastly, we're going to look at this series parallel circuit. So we have a 1K resistor in series with a 2.2K and 6.8K resistors, which are parallel. So this is series. This parallel circuit is in series with this single resistor here. So let's take a look at our voltages. So across the whole circuit, our voltage is 9 volts. The voltage across our 1K resistor here, oops, there we go, about 3.4 volts. The voltage drop across our 2.2K is about 5.7 volts and about 5.7 volts. So, like we've seen before in our parallel circuit, the voltage drop across both of these in parallel is the same. The voltage drop across our two series, so this effectively is one resistor, is different. Okay, and it depends on how big the resistor is. Now these two together are about 1.6K, so it's going to be, a little bit different, and it is. It's about 5 and a bit, and that's 3 and a bit. So together they add up to 9. So that's our voltages in this circuit. Now let's take a look at our currents. Okay, so we'll go to milliamps. We'll see what the current going into the circuit is by plugging ourselves into the inputs like so, and we're at about 3.4 milliamps. Coming out of the circuit, which should be the same thing. So we'll get this guy out of the way here. And we will check here. Oops, check here we go. Oops, I have that backwards. Let's do it this way then. There we go. 3.43 milliamps. So the current going in and out of the circuit is the same, which we kind of expected. Now I've got this kind of hooked up a little funny, because then I can take this guy out and measure the current going from between this and this parallel pair. If I were to just pull one of these out, I'd get just going through that one resistor. So I'm going to pull this guy out, and let's see what the current is going from our 1K resistor into our parallel set of resistors. Let's do that with the probe the right way around. And 3.43. So just like in a series circuit, this is acting as a series circuit. So these two parallels are one acting like one resistor, and 3.43, 3.43, and 3.43. Let's put this guy back in here. So now we can check to see what the current going through these two resistors are. So let's take this out and see what the current going through the 2.2K is. So we'll plug in here, and here, and here it's 2.6 milliamps. So it's low. So it's lower than the than our current going through the whole circuit. And let's try this one here. It gain will be lower, and it'll probably be considerably lower. 0.83 milliamps it looks like. Let's double check. Yep, 0.83 milliamps. Now if you add that up with our 2.6 here, we'll get the total current for the whole thing, just like we would in a regular parallel circuit. But what we can see is that this parallel piece is acting like one resistor in a series circuit. So the current at this point, and at this point, and at this point is the same. However, if we were to, as we measure the current going through these two resistors, it's going to be different, because just like it is in a parallel circuit, one will have more current going through the other if they're different values. Is equal to IR. We know the current is 3.4 milliamps, so E is going to be 3.4 milliamps times, in this case the resistance is 1000 ohms. So that's going to be 3.4 volts, which is indeed what we got. So that's working out quite well. Now this part, we know the effective resistance, basically the net effective resistance of these two in parallel. So that's also going to, so we just have to go, that's, and we know it's going to be 3.4 milliamps again. So 0.0034 amps, which is what we should use up here as well, of course, times 1662 ohms gives us 5.65 volts, which is pretty dang close to 5.7 volts. So even if we didn't originally know the voltage by measure, we can work it out, and we can actually work these out since we have the voltage drop there, and we can actually, since we worked out the current through the series bit, we could then use that to work out the entire network without doing any measuring. But we measured it, so that maybe saves a little time there. But what is the voltage drop across these? Well, again, we know the currents. Well, what should the current be? Let's look at it that way. We got our voltage drops at 5.7 volts, or 5.65 volts. Sorry, that's our theoretical. So V over R is going to give us the current. So for our 2.2K, it's going to be 5.65 volts divided by 2200 ohms, which gives us 2.57 milliamps. Pretty dang close to there. And we'll just come over here. For our 6.8K, we have 5.65 volts divided by 6800 ohms. And that gives us 0.8 milliamps, which is what we got. So it is possible to work these things out without measuring them at all, just by using Ohm's law, but you just have to be careful. Okay, so you work out what the total resistance of the circuit is. That'll give you the current going through kind of each part. You can then work out the voltage drop for our series bits. So 3.4 volts, the voltage drop here, and if we add these together, we should get 9 volts, more or less. And then we can work out everything else. It's all possible to do it with Ohm's law.